Our next reaction of ketones and aldehydes is actually just a reaction of aldehydes, and this is oxidation. So aldehydes, using the proper conditions, can be oxidized to a carboxylic acid. For example, if we have propanol and we treat it with chromic acid generated from potassium or sodium dichromate along with sulfuric acid in water, then this aldehyde can be oxidized to the carboxylic acid. But let's think about what's happening here. So even before our oxidizing agent, when we have an aldehyde in the presence of acid and water, this can be converted to the hydrate. And then it's the hydrate that actually gets oxidized to the carboxylic acid. When we talked about oxidation of primary alcohols, we saw that chromic acid would oxidize an alcohol to the carboxylic acid, whereas something like PCC, pyridinium chlorochromate, would oxidize a primary alcohol to the aldehyde. Rather than really being a difference in the reagent, the difference is in the solvent. With chromic acid, you are carrying out this reaction in the presence of aqueous acid, and so once the alcohol is oxidized to the aldehyde forms the hydrate, and then the hydrate is oxidized to the carboxylic acid. PCC is carried out in an organic solvent, such as dichloromethane. So there's no water present, it's not an acidic solution, and so once the primary alcohol is oxidized to the aldehyde, the reaction stops there because it's not converted to the hydrate, so then it's not oxidized. Furthermore, it turns out that there are many methods that can be used to oxidize aldehydes to carboxylic acids. You can use bleach, you can use potassium permanganate. For many aldehydes, air oxidation also occurs. And so if you open an old bottle of aldehyde, it might smell really bad because it has been oxidized to the carboxylic acid. One other interesting example is the oxidation of an aldehyde to a carboxylic acid using silver. In this example, we're using a silver salt to carry out this oxidation. There is a test for aldehydes called the Tollens test, and this uses a silver ammonia complex. As the aldehyde is being oxidized to the carboxylic acid, silver 2 plus is reduced to silver metal. And so this reaction leads to the formation of a silver layer on the glassware that's being used. And so you basically are making a mirror, and the formation of that mirror means that the silver was reduced, which means you had an aldehyde that got oxidized. Another important reaction of aldehydes and ketones is reduction. Now, there are two different types of reduction. The first one is where our carbonyl-containing compound is reduced to an alcohol. So an aldehyde can be reduced to a primary alcohol, while a ketone could be reduced to a secondary alcohol. Now, we've seen this happen with hydride reagents. If we have an aldehyde and it is reduced by sodium borohydride, for example, then this is going to give us a primary alcohol. If we used instead lithium aluminum hydride, we get the same thing. A ketone can be reduced either with sodium borohydride or lithium aluminum hydride to give, in this case, this alcohol, a secondary alcohol. Other functional groups, if we have a ketone as well as an alkene, lithium aluminum hydride or sodium borohydride will both reduce the carbonyl without touching the alkene. And finally, if we have an aldehyde or ketone as well as an aromatic ring, reduction with sodium borohydride or lithium aluminum hydride will result in the conversion of the aldehyde to the primary alcohol without affecting the aromatic ring. So In the case of aldehydes and ketones, using either sodium borohydride or lithium aluminum hydride will give the same products. Carbonyls can also be reduced by catalytic hydrogenation. Typically, it's not the same conditions as what you would use to convert an alkene to an alkane. There is a particular catalyst called Raney nickel. So treatment of an aldehyde or a ketone with Raney nickel and hydrogen can carry out a reduction. Our first aldehyde will be converted to the same alcohol, and our ketone will be converted to the same alcohol that we got with sodium borohydride or lithium aluminum hydride. Now, on a lab scale, it's going to be a lot easier to use sodium borohydride rather than Raney nickel and hydrogen, but on an industrial scale, it's much more common to use catalytic hydrogenation. And then there is a difference when we're talking about different functional groups. Sodium borohydride or lithium aluminum hydride will reduce a ketone without touching the alkene, but catalytic hydrogenation using Raney nickel will reduce both. If we have an aldehyde or ketone along with an aromatic ring, then the aromatic ring still is not affected, unless really forcing conditions, really high pressure and heat are used. So the difference between the hydride reducing agents and Raney nickel really comes into play if you have an alkene in your starting material. There's another type of reduction of aldehydes and ketones that's actually a deoxygenation. So rather than the carbonyl being partially reduced to the alcohol, instead the carbonyl can be reduced all the way down to a methylene group, so down to a CH2. So oxygen has been lost. We saw this in our chapter on the reactions of aromatic compounds. After doing a Friedel-Crafts acylation, for example, this carbonyl can be reduced all the way down to the methylene. And this is the Clemmensen reduction, which uses a zinc-mercury amalgam in the presence of HCl. This reaction has a complex mechanism that's happening at the metal surface, so you're not responsible for the mechanism, but you are responsible for knowing what happens. Another method to carry out this reduction and deoxygenation is to use what's called a Wolff-Kishner reduction. This one uses hydrazine in the presence of acid, followed by hydroxide. In this case, the carbonyl is again reduced to the methylene. Why do we need two different sets of conditions? Well, in the case of Clemmensen, typically this is done with more concentrated acid and heated up. So if you have other functional groups in your molecule that would react under strong acid conditions, then the Clemmensen reaction might not be the way to go. Instead, this is mild acid followed by basic conditions. And so some functional groups that would be sensitive to this would withstand these conditions, and vice versa. We talk about the Wolff-Kishner reduction in this chapter because it goes through the formation of a hydrazone, which is a specific type of imine. So if we think about the mechanism, we can imagine either one of these nitrogens acting as a nucleophile, sharing electrons with the carbonyl carbon, and this is going to lead to an intermediate that looks like this. And then with the loss of water, this is going to give an imine. Now, an imine made specifically from hydrazine is called a hydrazone. But still, we're just talking about the formation of an imine, so this mechanism is the same as what we have already seen. From here, in case you're interested, what happens when we add base? Hydroxide can grab off one of these protons. I'm going to stop with the color coding now. We already had one lone pair, now we have a second lone pair, and the nitrogen has a formal charge of -1. This can react with water, where these electrons can come in here, pushing these electrons out here to grab a proton, and that gives us this intermediate. So notice the double bond has moved from carbon-nitrogen to nitrogen-nitrogen. Another equivalent of base can grab off this proton, putting these electrons onto the nitrogen. And now nitrogen gas is given off, giving us this intermediate, and then grabbing a proton from water gives us our final product. So the first part of the Wolff-Kishner reduction, the formation of the hydrazone, this is analogous to the other nucleophilic addition reactions we've seen. And then the actual reduction part of it, that's something completely different. I wanted to show you just for your information. So this brings us to the end of our chapter on ketones and aldehydes. And we looked through naming, structure, properties, and spectroscopy. We saw a variety of ways to prepare ketones and aldehydes, so Friedel-Crafts acylation and from alcohols by oxidation, but they can also be prepared from alkenes and alkynes, or from acids, esters, acid chlorides, and nitriles, so a variety of methods. Furthermore, we looked at different reactions of ketones and aldehydes, including nucleophilic addition, both by Grignard reagents, hydride reagents, but also reversible nucleophilic addition reactions. We also saw the Wittig reaction, oxidation of aldehydes, and reduction of both aldehydes and ketones, either to alcohols or to a methylene.